When we use the Euler-Cromer method to predict the motion of an object, we need a way of calculating the force that acts on the object at any location and at any time. But in many applications in physics, it's better to work with the potential energy that the object experiences instead of the force. The potential energy is a scalar, whereas force is a vector, automatically making it easier to work with. And potential energy offers the simple visualization that objects tend to roll downhill. Fortunately, there's a direct relationship between potential energy and force that allows us to use the Euler-Cromer method with just a few modifications. When you have a function for potential energy, you simply take one derivative with respect to x, y, and z. Then you multiply each of these derivatives by the associated unit vector, which we'll call x hat, y hat, and z hat. These are also sometimes called I hat, j hat, and k hat. Then you add these three vector derivatives, obtaining what's called the gradient of the potential energy. Finally, to get the force, you just multiply the gradient by -1. This negative is needed in order for objects to roll downhill. The gradient is fairly easy to calculate in a computer code. To get the derivative with respect to x, you simply evaluate the potential energy just to the left and just to the right of the point you're interested in while keeping the y and z values the same. Then you divide the difference of these two results by 2 times the amount you stepped in each direction. There's a similar process for obtaining the derivatives with respect to y and z. Again, you take a step to either side of the point you're interested in, then divide the difference by 2 times the step. And again, you keep the other two position coordinates at the same value. We've set up this gradient calculation in this code, which is available at a link in the description below. The potential energy we'll work with models a spring that can stretch and rotate in all 3 dimensions. Here we evaluate the 3 derivatives we need. Again, note that we keep 2 position coordinates the same while we slightly adjust the one we're interested in. Then we collect these 3 derivatives in a vector and multiply by -1 to get the force. The loop creating the Euler-Cromer method is the same as we've seen before. The only difference between this code and our previous version is that there's one extra step in calculating the force. The results show an interesting feature: oscillations in a plane parallel to the ball's position vector and momentum vector. You should now be able to simulate the motion of an object under the influence of a potential energy. Use the code in the link in the description below to apply the Euler-Cromer method to these potential energies and initial conditions. Which of them shows motion constrained in a plane? Next time, we'll see how angular momentum is kept consistent in our results.